Now we conduct an experiment to determine the Fermi energy of copper. Fermi energy is the energy corresponding to the highest occupied energy level by an electron at 0 degree absolute. Fermi level is a demarcating energy level between completely occupied energy levels below the Fermi energy level and completely empty energy levels above the Fermi energy level. Suppose heat is supplied to a metal at a particular temperature. It is the electrons closer to the Fermi energy level which absorb this energy and move up to the levels above the Fermi energy level. But these electrons cannot stay there for more time, and by a de-excitation mechanism these electrons get back to their original energy levels below the Fermi energy level. That is, there is excitation and de-excitation processes which take place across the Fermi energy level, and hence Fermi energy also can be thought of as the average energy of the conduction electrons. We now perform the experiment to determine the Fermi energy using the circuit as shown here. So, we have a series connection of the constant current source, the milliammeter and the copper coil which is immersed in hot water bath, which is fitted with a thermometer. Either it can be a regular thermometer or a digital thermometer which is used by the digital multimeter. Then we have a voltmeter which is connected across the coil. So, we now rig up the circuit in the following way. So, we close first of all the gap and connect the constant current source. We connect the milliammeter such that the positive is connected to positive and negative is connected to the negative. Then parallel connection of the voltmeter such that the positive is connected to positive and negative is connected to the negative. Then the copper coil is inserted in the circuit at the designated place, and the coil is immersed in hot water that is kept in a test tube which is kept in a hot water bath. Electric water heater is used to generate the heat the water and then generate the heat. So, we now have to wait till the temperature of the coil rises to say about 80 degrees centigrade. We can also use the ordinary thermometer to measure the temperature. So, we need to wait till the temperature rises to 80 degrees centigrade. You can notice that there is a display in the milliammeter as well as in the millivoltmeter which are now changing in their readings, but we will not record these. So, we continuously monitor the temperature reading using the digital multimeter. So, you will see that the temperature is rising gradually, and now it is almost touching 80 degrees. So, when it has touched something like 77 degrees, we have switched off, so that with the heat already there available to the coil, it rises to the required temperature of 80 degrees centigrade. So, when once it has touched 80 degrees centigrade, we note down the milliammeter reading and the millivoltmeter reading as indicated in the kit. Yes, now we have reached 80 degrees centigrade. The readings are 46.7 milliampere and 22.6 millivolt. So, we record these readings and we can lift up the coil to a higher level away from the hot water bath, so that the coil gets cooled faster as per Newton's law of cooling. If the difference in temperature between the hot body and the surroundings is greater, cooling will be faster. So, now we wait till the temperature climbs down to 75 degree centigrade. So, when it is 75, we record the reading, and when once it touches 70, again we take the readings of milliammeter and the millivoltmeter. Like this, we have to continue till the temperature has come down to 40 degree centigrade, and we have recorded all the readings as indicated in this tabular column. So, with this we will calculate the value of resistance of the copper coil at various temperatures using the simple Ohm's law formula, R equals V by I. So, the resistances are recorded here, are calculated here. Then we will notice that as the temperature decreases, resistance has also decreased. Then we plot graph of resistance versus temperature in Kelvin. Resistance is plotted along the y-axis and temperature along the x-axis. Then we find the slope of this plotting, and we have to insert the value of slope and square it and insert in the Fermi energy formula, which is given by B into slope square divided by 1.6 into 10 power minus 19, which gives us the Fermi energy value in electron volt. Here B is nothing but Ne square pi a r square divided by L root of 2 Me whole square, where N is number of electrons per unit volume, which is also known as electron concentration. E is electronic charge, 1.6 into 10 power minus 19 coulomb, pi is a constant 3.14, A is lambda into T. Lambda is nothing but mean free path of copper that is available in the catalogue, and we determine that value, and R is the radius of the copper wire, L is the length of the copper wire, Me is mass of the electron. So, we have to determine B separately and insert it in the formula here, so that it is easier to determine the value of the Fermi energy of copper in electron volt.